So let's look at a problem called Newton's solid of minimum resistance. So the idea is that if we have a projectile, let's say a bullet, and it's travelling in the y direction, the question is, what shape do we have to make the head of the bullet in order to minimise the air resistance? Now Newton started off by assuming that air resistance is directly proportional to v squared, so we'll just stick with that. But we'll get back to that in the next slide. So we've got three options here that we've got drawn out. If we said, for example, that the bullet was just a flat surface, so the head of the bullet here wasn't curved, it was just a flat surface, then we would have a maximum air resistance. So we've got that drawn out here. We imagine the air travelling onto that surface, so all of the air would hit the surface if it was just hitting it head on like this. Now if the surface was tilted slightly, not all of the air would hit the surface, so the air resistance would decrease. And then if you were to think about the surface being at 90 degrees, then none of the air would actually hit that surface, so the air resistance would be a minimum. So we could see here we'd have a maximum here, we would have a minimum here, and we'd have something in between in this point here. So I've drawn the tip of the bullet out here just to see where these three are. So if we were to look at the edge of the bullet, well, we would have a minimum air resistance at the edge, because if you imagine going out just a little bit beyond the bullet, then there wouldn't be any air resistance because the bullet wouldn't be in contact with that part of the air. So it only gets in contact just at the very edge here. So we would have a minimum air resistance here, and this would be what we see in the first drawing here. Now if we went to the other extreme, and we could say that if we were travelling in, say, this direction, which is, say, in yellow, then all of the air would be hitting the head of the bullet at this point. So this would give us the maximum air resistance, and we'd have all values in between along this curve. So if we take up an example here, if we were to take the normal to the surface, so that's the normal in yellow, then the amount of air resistance at this surface here would be dependent on the angle between the normal and the direction of travel. So say for example in this point here, the normal's in yellow, the direction of travel is in pink here, and the angle between these is 90 degrees, and that's going to give us a minimum air resistance. So we could plot that in a little graph. So there's a little graph here. We could go to 90 degrees and the air resistance would be a value of 0. Now if we were up at the top point here, the angle between the direction of travel and the normal is 0 degrees. They're in the same direction, so that's really what we've got here. Then the value of that would be a maximum, so we've put down a maximum value here. And the in-between point here, the air resistance would be some value in between. So the value in between here would be the normal component here of this direction. Okay, so really if the air resistance is in this way, it would be the normal of the air resistance. So really what we're looking about is the angle here between the normal and this component here of direction. So what we have is a dot product. So the air resistance is dependent on the angle between the air that's hitting the surface and the normal to that surface. So we'll go ahead and we'll show that mathematically on the next page. So we said that the air resistance AR is directly proportional to the velocity squared, but we also know it's dependent on the angle in which it hits the bullet. So if we were to imagine taking a small section of the bullet here in blue, if we were to draw a tangent to a point, then we would know the normal to that tangent would face in this direction here. And we would be interested in the direction between the normal here and the actual direction of travel. And we'd be interested in this little angle between them. So that's the normal there, and that's the direction of travel, and we've got the little angle in between it. Now that little angle there is the same as this little angle down here. Okay, so just convince yourself of that little geometrically that the angle between the direction of travel and the normal is the same as this angle here. So if we were to call this angle large angle phi, then this angle in here would be 180 degrees, or pi minus phi. So it means that the air resistance then at a single point would be velocity squared times the cos squared pi minus phi. So it's cos squared because we're dealing in terms of velocity squared. So that's really just the dot product. Now that's only for one single little point. If we were to look at the bullet, it would be a circumference here round like this. Okay, so if you imagine the bullet's getting cut along this axis here, we take one particular point and we could draw the circumference round that bullet. So in order to get the air resistance round the entire bullet there, if we think about this distance here as a value of x, then the circumference is just going to be 2 pi times x, assuming that we're dealing in radians. So that would just give a value of 2 pi x. So that's the air resistance round a small section here of circumference. But of course, that's only one of those little sections. We've got to do it for every single one of the sections all the way down the length of the top of the bullet. So that is, we've got to integrate from 0 to x of all this function with respect to dx. And that will give us the total air resistance AR. Now we've seen before that we can write things here in terms of infinitesimals. So if we were to think about this here as just an infinitesimal section of the bullet, then we could think about this as dy, dx and ds. Of course the ds would actually be a straight line. So we could say our dx squared plus dy squared would equal ds squared. So therefore we can divide throughout by our dx, and we can take the square root, so we'll get 1 plus y derivative squared to the power of a half. Now we can also take the reciprocal of this, and we'll take the reciprocal of that side, so we get dx by ds is 1 upon root 1 plus y derivative squared. But if you look at this value dx by ds, well that's just our value dx here and our ds. So that's just going to be the cos of this little angle here, which is pi minus phi. But equally we could say that the cos of an angle is equal to the cos of this angle here, phi, the same is equal to minus the cos of this little angle in here. Okay, so we could really write that then as minus cos phi. So we can say our 1 upon root 1 plus y derivative squared is the same as minus cos phi. So therefore we could say that if we were to square both sides, we could say minus cos phi, minus cos squared phi would be 1 upon 1 plus y derivative squared. So we can then put this back into our equation up here for the air resistance, and we'll have our air resistance then, we'll take out the value of our v squared, we'll take out our value of our 2 pi, we'll have our negative sign in here, and our cos pi minus phi, we can put that in as cos squared pi minus phi, we'll just replace that with our cos squared phi. So finally we can leave the values of our v squared 2 pi out as constants, because we're assuming that the velocity is a constant value. And we'll just be left with the integral from 0 to x of minus x upon 1 plus y derivative by dx. And again I've got that written down here. So in terms of our functional, this is the thing we want to minimise. And we know we've got a function of the independent variable x, and the only thing that's dependent on that value of x is the y derivative. So it was a function that's got an explicit dependence on y derivative. So we can simplify the Euler-Lagrange as partial f by partial y derivative equals c. So let's go ahead and we'll do this on the next slide. So we'll go through our differentiation here. We can take the 1 plus y derivative squared up to the top, becomes 1 plus y derivative squared to the minus 1. When we do the differentiation with respect to y derivative, we'll have our minus 1, so the minus cancels with the minus, makes us a plus. X remains as is. We'll have 1 plus y derivative squared to the minus 2, and then we differentiate what's inside, so that becomes 2y derivative equals that constant. So we're left with the 2xy derivative all upon 1 plus y derivative squared all squared is equal to the constant c. Now we're going to solve this parametrically because that's what's been done in the book, so let's just work through this and take our time. So if we replace y derivative with a value of p, and then we transpose this thing for x, then we get the x equals c upon 2p 1 plus p squared all squared. And then we note that y is going to be the integral of p dx, because we've just got this y derivative equals p, so y is going to be the integral of p dx. And we can replace the dx with what we have here. So the dx will be c upon dp 1 plus dp squared all squared. And that's all we're going to be multiplied by p. So you're going to be left with y is equal to this term here. Now there's a squared term here, so there's going to be 3 terms multiplied by this. So we'll do each of them separately. So we'll end up with a y1, y2 and y3. So the y1 term is the integral of cp all upon dp. And that's going to give us our value of minus c log p. And the second term here is going to be cp upon dp 2 dp squared. So that's the same as the integral of 2cp by dp, which is the value of cp squared. And the y3 is going to be the integral of cp upon dp, dp to the 4, which gives a value of c 3.4 p to the 4. Okay, so take your time and work your way through these and convince yourself that you actually get these here. So let's finish it off on the next page. So all we need to do is just add the 3 sections up and also add in our constant of integration. So we'll call our constant integration a. Then we add the 3 up and simplify. We get our value of c into minus log p plus p squared plus 3.4 p to the 4. And the value for x is c upon p 1 plus p squared all squared. And what we have there is the parametric curve of minimum resistance. So it's a parametric curve, and we'll go and we'll look at it in the graphical calculator. So a bit of mathematics involved in that, and a bit of work in order to get it into the format that we're looking for. So let's have a wee look at it in the graphical calculator. So put the function that we've just derived into the graphical calculator, and we can see that as we were adjusting this value here, you can see that we're going to map out a curve here, which in effect would be the top of the bullet. So we would be generating top of the bullet by the curve that's generated by those 2 little markers. And that would be the curve of minimum resistance, assuming that the air resistance is directly proportional to the velocity squared, which is not necessarily the case, but it helps us anyway to understand a little bit of calculus of variations. And this is the way that Newton originally derived this in his Principia. So thank you for listening. I'll get you on the next video. Goodbye.